Hey everybody, this is Mr. Schaefer with Calculus Video Lesson 1.3, an introduction to definite integrals. And to start off, I'd like you to just notice this definition of what a definite integral in calculus really represents. Sort of graphically or symbolically, it's the area underneath a function, and we define that as the area between the function and the x-axis, or the independent axis. And specifically because it's area, it's the product of the x and y variables. So keep that idea in mind, the product of the x and y variables. So here's an exploration of how we can kind of compute definite integrals and how we can approximate them in real world problems, in this case involving the speed of a car. So we have here a picture of a velocity function in number 1. And it says that the highway speed is 100 feet per second to pass a truck, but then after we pass that truck, the speed slows down to a more moderate 60 feet per second. And we see that here in the graph. So the vertical axis has the units of velocity, feet per second, and the horizontal axis is in time, seconds. Now, the first thing I want to do here is answer the question, what is the velocity between time 30 and time 50 seconds? If you notice, that's really level at about 60 feet per second. But then the question about distance arises here. How far do you travel in the time interval from 30 to 50 seconds? Remember that the distance formula is simply rate times time. So if I'm traveling 60 feet per second, for 20 seconds, then I have a total distance traveled of 1,200 feet from 30 to 50 seconds. That question can actually be represented by the area of the rectangular region in this graph. And you can see that kind of here highlighted in yellow. I have one dimension of my yellow rectangle here as 20, which represents the change in seconds. But then the speed, or the velocity in this case of the car, that height is 60. So there's the rectangle, which has a base times height of 20 times 60, representing rate times time of 20 times 60, or the distance traveled, which is 1,200. So what I might propose that you look into is a little unit analysis activity, where we have feet per second on one side of my square in the grid, and then I have seconds on the other side of the square. And when you multiply those two together to get area, base times height, I'm actually doing feet per second try that again. There we go, feet per second times seconds. Here's the unit analysis. The seconds will actually cancel out, and we're left with simply feet, or distance that the car traveled. And that's great, but what if we have a function that's curved and not piecewise linear? So question 3 says that the distance you travel between 0 and 20 seconds can be found in the exact same way by finding the area of the region bounded by the curved velocity graph and the t-axis. But because we have a curved section here, now I've got to actually do a little bit of creative square counting. Notice that one square unit in the grid isn't really equal to one square unit, because the scale has 5 across the horizontal and then 10 across the vertical. This little dark blue square that's shaded in here has really a 5 by 10 or 50 square unit value to it. And then I have these little tiny regions up above that are partial squares. This might be 0.6 squares, maybe 0.1 squares or 0.9. Here's a little corner that I'm going to call 0.3, another 0.9, and so forth. So I'm doing this kind of partial square approximation in that grid to try to figure out how much area falls below the curve. Now, if you count up all of the squares, including the little partial pieces from 0 to 20, I counted approximately 28.6. And maybe you estimated and got 28 or 28.1, or maybe you got something closer to 29 or 30. And it's an approximation, that's okay. Each square's area, like I said, was 50. So knowing that, I'm going to come up here to question number 4. How many feet does each small square represent? Well, that would be the 50 square feet. So how far did you go? Well, 28.6 squares. Each square is about 50, giving me a total distance of approximately 1,430 feet. That's an approximation. If your square count varies, maybe you have a little bit less than 1430 or a little bit more than 1430, and that's okay. So this idea of the definite integral, again, is the product of the x and y variables. I'm going to bypass number 5 for just a moment and show you one last example. In number 6, we have a picture, a graph, that shows the cross-sectional area of a football. So the y variable is actually in square inches across the vertical, and the x-axis represents the inches from one end of the football to the other end of the football, so inches singular by itself. Estimate the definite integral of y with respect to x. So if I go from 0 all the way to 12, I'm looking for the area under the function curve in this case. I'm going to square count all of this, but let me first examine one of these little grid squares. It looks like I have a length of 1 across the base, but the height of each one of my squares is going to be 5. So there's a 5 by 1 square. I'd like to count how many squares there are under the function. Notice I have partial squares. So maybe like a 0.3. This looks like a 0.6, maybe a 0.6 or a 0.5. And here's maybe 0.5, half of the square, maybe a 0.2 down below. So I'm looking for the partial squares as well as I do my total square count. Now, I counted approximately 45 squares. And each area of one square is 5. 45 times 5 gives me approximately 225. And I'm interested in the units right now. So think about it. You're taking inches times inches squared. Inches times inches squared would be inches cubed. So 225 cubic inches, what I essentially found was a representation of the volume in cubic inches of that football. So what do you suppose the definite integral represents? I would suggest the volume of the football. In cubic inches from 0 to 12 inches across. Now we've got to be very careful when we apply the meaning of a definite integral that we always go back and talk about the bounds or the start and the finish of the integral. Don't just say that 225 is the volume of the football, but say that it's the volume from the 0 inches to the 12 inches, from the lower bound to the upper bound. And likewise, this distance problem over here, I don't just want to say 1,200 feet. I want to say 1,200 feet traveled by the vehicle from 30 to 50 seconds. So always go back and talk about the bounds, interpret the bounds, interpret the endpoints of the region that you're computing the definite integral across. So that's a brief introduction of a definite integral in calculus and just 2 applications of how it works by counting the squares and approximating the area underneath the function representing the product of the x and y variables.